Hello everyone. Today, I'm going to show you how you can leverage Dyad's model discovery capabilities to identify missing physics inside of your models. What we'll do is we'll create a simple pot model, incorporate a neural network component into that model, and then we'll train it in order for it to match up with our experimental data. So here inside of VS Code, I'm going to open up my command palette, type out Dyad and select Dyad, create component library. When prompted, I'll give my component library the name model discovery, and I'll save my component library inside of this folder on my desktop. Here inside of my project library, I'm going to open up the Julia REPL. I'll enter the package manager by hitting the close bracket key, and then we're going to add 4 packages to our project. We'll add thermal components, block components, Dyad data, and Dyad model discovery. Next, I'll instantiate my project. Okay, I'm going to hit backspace key to exit the package manager. And now we can start creating our models. So on the left side in the Dyad folder, I'm going to create a new file. And I'm going to name this file simplepot.dyad. Inside of this file, I'm going to paste the definition for my simple pot model. What I'm going to do is I'm going to go ahead and collapse. You'll note that we have a bunch of different components right here, and they all have some graphical data associated with them. Okay, so what we can do, because it has this graphical data, we can go ahead and render this diagram to take a look at this simple pot model. And there we have it on the right side. So I'm just going to go ahead and collapse all this graphical data so it's a little bit easier to look at the model. Okay. So I'll go ahead and go like this. Here we have our simple pot model. Let's take a look at the various components inside of this model. So we have a heat input right here, which is a sine component from the block components library. And that's what we see right here. Next, we have a source component, which is a prescribed heat flow component from the thermal components library. And that's right here. And then we also have a pot right here, air component, which is a thermal conductor right here, a environment component, which is a fixed temperature component from the thermal components library. And then lastly, down here, we have a temperature sensor component. Okay. And just want to note that our pot is, of course, an instantiation of a heat capacitor. And then we also have these connect statements down here, which are all these connect lines that you see, which connect all our components together into one coherent model. So this is our simple pot model. We haven't incorporated the neural network into this model yet, but let's just go ahead and run an analysis on this simple pot model and take a look at whether or not the results match up with our experimental data. So in the same file, I'm going to define an analysis for this simple pot. So this analysis will be called simple pot transient. This is an extension of the transient analysis type. In other words, this inherits everything from the transient analysis type. And the model that this analysis is using is, of course, the simple pot model that we've defined right here. Okay, so let's go ahead and run this model. So what I'm going to do is I'm going to create a new file, and I'm just going to call this file main.jl. And in this file, I'm just going to include the Julia code we're going to be using to run today's demo. So the first thing I want to do right here is bring my project into scope. So I'm going to do a using model discovery statement. And then let's go ahead and include some of this other code right down here. Next, we're going to bring in Dyad interface, Dyad data, as well as plots. Here, let's go ahead and go through our simple pot analysis. Okay, so the first thing we do right here is we run the simple pot transient analysis that we just defined right over here. Now that that analysis is done, we'll call this artifacts function in order to pull out this simplified system and place it inside of this model variable. And what that's going to allow us to do is it's going to allow us to decide which specific signals to plot. And then what we do is we're going to pull out this data from the Dyad data set. What we're pulling is we are looking for the pot plate data associated with this tutorial. And for the data we're pulling out data that has an independent variable associated with time and a dependent variable associated with pot temperature. So this right here, this is our experimental data that we're comparing our pot analysis against. We build that data into a data frame right there. And then right here, we can go ahead and plot the solution to our analysis, right? So we carried out the analysis and stored it inside this sol1 variable. So here we are plotting sol1, and what we are plotting from that is we're plotting the temperature of the pot from our model run. And then the second line right here, what we're going to do is we're going to also plot the experimental data alongside our simulation results. So here, when I run line 16, we can see the temperature that the pot experienced throughout the simulation. And then I'll run line 17, and we can see the real experimental data also overlaid on this graph. So we can see here that the blue line, our model, does track the experimental real data okay, but we can also see that there's gaps in between, right? So our pot model, our simple pot model, is missing some sort of complexity that isn't captured, and we can see that by the difference between our simulation and the experimental data. Okay, so what we're going to do now is we're going to create a thermal neural network component that we're going to use and incorporate inside of our pot model. And that neural network component is going to be trained against the real data. Okay, so what I'm going to do here is I will create a new file in my Dyad folder, and I'm going to name this thermal_nn.dyad. And here I will paste the definition for our thermal neural network. So here, what we can see is we have a component called thermal neural network. This component has some parameters, n input equals 2 and n output equals 1. So what that means is our neural network is going to have 2 inputs and 1 output. Right here, we set up a component called NN, which is an instance of a neural network block from the Dyad model discovery package. And then we can see that we feed in these various arguments to set up our neural network. All right. And of course, we see the number of inputs and number of outputs variable inputted here. We have some parameters associated with our neural network for temperature, the temperature range, as well as unit conversion factor. And our thermal neural network has 2 nodes. These nodes are connectors, which allow this neural network component to be connected to other components inside of our model. And then down here, we have the relations or equations that will be preserved by this component. So we see we have some initial setup for this block. We can see right here that the neural network inputs are mapped to the temperatures at the 2 nodes, right? So we set up here, we have node A and B, and you can see here that the first neural network input is a normalized signal of node A's temperature, right? The idea is we are normalizing these inputs so that their range is 0 to 1, and we normalize it using these 2 parameters right up here. And then finally, down here at the bottom is where we connect the neural network's output. You can see here that it's outputting heat flow rate and that there is a feedback loop, since we can see that one of the inputs up here is mapped to node AT, and we can also see node AT appearing right down here as a relation to the neural network output. Okay, so what the neural network is going to be doing here is it's going to be learning and encoding a new state. Okay, so now we have this thermal neural network component. Let's incorporate it into our pot model. So what I'll do here is I'll create a new file inside my Dyad folder, and I'll name this file neuralpot.dyad. And so what we want to do here is let's just copy our definition for the simple pot, and we'll paste it over here for the neural pot. And this will be our starting point. So I'll rename this to a neural pot and hit save. Okay, so this neural pot is of course identical to the simple pot as of now. We haven't made any changes yet. But let's go ahead and incorporate the thermal neural network component into our neural pot. Okay, so what I'm going to do is I'm going to render the diagram right here. And here, what I want to do is I want to place the thermal neural network component that we just created, and I want to stick it right here inside of our model. Okay, so what I'm going to do, and you'll notice that as I modify the model over here, we'll see changes in the code-based representation on the left side as well. Okay, so you can modify this on either side, the left side or the right side, and the other side will update accordingly. So right here, what I'm going to do is I'm just going to move this source block over to the left, and then I'm going to delete this connection right here. We want to add in that thermal neural network, so I'll right click, select add component, go to my project right here, model discovery, and add in the thermal neural network. I drag this thermal neural network right down here, and then I'll connect everything. I'll connect the source node to the thermal neural network's node A, and then I'll connect the thermal neural network's node B to the POTS node. So now if we take a look at the left side again, inside of our code definition for the neural pot, we'll see that this is pretty much still similar to the simple pot, except for the fact that it now has this thermal neural network component inside of it. So we haven't trained this neural network at all, right? We just incorporated it into our neural pot. So before we do any kind of training, let's go ahead and just simulate this neural pot to look at what the response looks like. Okay, we just want to confirm here that the loss function is reasonable. So in this neuralpot.dyad file at the bottom here, I'm going to paste this definition for neural pot transient, and this is extending the transient analysis type, and the model it uses is of course the neural pot. Okay, so let's go ahead and run this analysis. So I'm going to go back to my main Julia file right here. And so now we're doing with the neural plot. And so prior to training, let's just run this analysis and then plot the results against the experimental data. We'll run line 27 to once again pull out the simplified system. And then just like before, what we did with the simple pot for this neural pot, let's just go ahead and plot its pot temperature against the experimental data. So here we can see the neural pot's temp prior to any training against the real data. Okay, so we see that it does an okay job, but not a great job. Again, we can see these gaps in between the experimental and our model. But what we just wanted to confirm here that the model is reasonable and that this loss function, or the loss in between these two, is relatively small, something that we can solve for. Now that we've done those pre-training observations, right? We haven't trained the neural network yet, but we just wanted to see what it simulated like. Let's go ahead and do the training. Inside the neuralpot.dyad file at the very bottom here, I'm going to include an analysis for this training. So here we have an analysis called neuralpot training analysis. This extends the neural network training analysis type from the Dyad model discovery package. We can see here that the data that it's using to train is the exact same data that we were using earlier to plot right over here, right? It's just the pot plate data with a timestamp and the temperature. And then we have a few other arguments to set up the training analysis here, dependent variable names, which algorithm, calibration algorithms, optimizer, and so on. And what's going to happen is once this training completes, we're going to save the weights or parameters of that neural network and save it inside a CSV file called r1.csv. And we'll use that a little bit later. Okay, so what we're just going to do is just run this analysis. Okay, let's run this analysis to train the neural network and discover the network's weights. So let's go back into the Julia script right over here, and I will call the training to this command right here. Okay, great. Looks like the training is completed. So down here in the output, we can see the weights or parameters to the neural network that the training concluded. We've done the training. Let's take a look at some artifacts of this training. So first, let's go ahead and just take a look at the convergence plot right here. And there we have it. So we can see that the training went through 10,000 iterations and that the loss decreased. In other words, the training accuracy increased as we move down the iterations. All right, so this is a good thing. We're getting a better trained model as we continue to iterate. Now let's take a look at the calibrated simulation results. So what this is we're going to take a look at the simulated neural pot model if that neural network inside our neural pot model used all the weights that were discovered during the analysis, right? So I'm going to say that again. So just all the weights down here that we discovered during our training analysis, if we were to stick these weights back into our neural pot model, what would we get? What are the results we would get? So we're going to answer that question right here, right? So we're going to pull out the calibrated simulation, pull out the time vector from that simulation, as well as the simulation temperatures, and then we'll go ahead and plot it. So here we've plotted the neural pot's temperature signature throughout the simulation post-training, right? So using the neural network weights that were learned during the training. And then we plot that against the experimental data. We can see that there is great overlap between our model, our trained model, and the real data. All right, so we've successfully trained our neural network. So the last thing right here is we're going to do some symbolic regression so that we can identify some candidate models for the neural network. So recall our thermal neural network has 2 inputs and 1 output. Okay, so 2 inputs and 1 output to the thermal neural network. So what I'm going to do over here, the first thing I'm going to do is I'm going to run line 47, and that's just going to export our neural network weight to this CSV file that you see here on the left side. And then we need to run an analysis to discover the UDE. So back over here in the neural pot file, I'm going to include the neural pot UDE analysis right here. So this is what we're going to run next. Okay, so this neural pot UDE analysis is a inherits from the symbolic regression UDE analysis type from Dyad model discovery. You can see here, it's using the same data set as before, and the training result that it's going to be using is the r1.csv file. Okay, so let's go ahead and run this symbolic regression, this UDE analysis right here. We can see here that the UDE analysis run has completed, and we can see our result right down here. So let's go ahead and move to this thermal neural network file one more time. So here we can see that the system level UDE results identified 4 candidate models for the neural network, right? And here are the candidate terms for that neural network. We can see here, one possible candidate is P1 times input 1 minus input 2, right? So this is just P1 times input 1 minus input 2. Okay, and if you're wondering, okay, well, what are the inputs? Well, input 1 and input 2 were identified right up here inside of our neural network. So we know that the input 1 and input 2 are defined like this. Okay, and then what's P1? Well, P1 is identified right down here in the parameters. P1 in this case is 29.98. And the cost value of this function is this right here. Okay, so again, I'll just say that one more time. So there's 4 candidate models. The first candidate model for our neural network is P1 times the difference between input 1 and input 2. P1, of course, is this value right here. And then we have more candidate models, right? This candidate model, the second one, takes input 1, adds it to P1, and then subtracts input 2 times P2. And then we can see P1 and P2 right down here, and we can see its cost function right there. Okay, so the idea is, if you were trying to identify the physics for this neural network block, if you wanted to identify the candidate model with the lowest cost, this is the one you would go with, right? Because the first candidate has the lowest cost. But the exercise here would be, it would be on the engineer to understand what kind of system they're trying to model, and they would look at these candidate models and they would have to identify the one that not only has a low cost function, but also makes physical sense in the context of whatever model they're trying to create. Okay? And that's it for today's demo. What we did today was we created a simple pot model, and we took a look at the difference between the simulation results from this model and the difference between the simulation results from the simple pot model and the real data. Then we created a thermal neural network component to incorporate into the neural pot. We saw that initially, prior to any kind of training, the neural pot's temp does an okay job of tracking the actual data. And then we move to the actual training. We can see that the convergence plot and the loss improves over the time and over iterations. And then we go back, plug the learned neural network weights back into the neural pot, and we see that the simulation results from that pot is very close to the experimental data. And then finally, what we did was we performed symbolic regression analysis to identify possible candidate models for that neural network that we trained. Thanks for joining today, and I hope you learned something valuable.